I'm Tegan Taylor. I'm a journalist here at the ABC Science Unit, and with me is astrophysicist, cosmologist, and just general awesomeness, Professor Tamara Davis from the University of Queensland. Welcome.
Thank you so much.
We're taking your questions on black holes today, and by we, I definitely mean Tamara. She's the expert, and she can answer anything that you have to throw at her.
That might be an exaggeration, but we'll see how we go.
But let's start with some basics. What are some of the biggest misconceptions that you encounter about black holes?
So, black holes, very, very cool things, but people tend to think of them as like cosmic vacuum cleaners that just suck absolutely everything in. And that's not exactly true. Like, you can go close to a black hole and not fall in if you have your jets going, or you can happily orbit a black hole. It's just if you get too close, then you can't escape. And that's probably the thing I find most people are really fearful of black holes, just sucking everything in.
So they're not exactly a hole.
No, it's not a hole in space. It's almost the opposite. It's something that's super, super dense. So it's not empty at all. That's probably the worst misnomer ever. But what it does look like is a black hole in space. Because if you were to see a black hole, you wouldn't see light coming off it. It would just look like a silhouette of darkness against whatever was behind it. And that's sort of probably one of the sort of cool stereotypical features of a black hole.
Right, so when we talk about black holes, two words or two phrases that you often hear are singularity and event horizon.
Yes.
Very great, like science fiction-y sounding words. What do they mean?
Okay, so let's start with the event horizon, because that's probably the easier one.
Okay.
The event horizon is the point of no return. It's just an imaginary sphere around the singularity at the center. And the imaginary sphere, it doesn't have a substance to it. You couldn't stand on it or anything like that. There's actually really nothing there. But it marks the point that if you go within the event horizon, gravity is going to be too strong to let you ever escape. You can't escape, light can't escape, no rockets firing will ever do you any good. You're going to get sucked down into the middle. And
right.
It's called an event horizon because if you're watching from outside, any events that happen inside that horizon, you'll never see.
Right, so it's literally like you can't see past the horizon on Earth.
Yeah, so you've got the horizon on Earth, which is just a sort of spatial horizon. You can sort of only see to a certain edge of the ocean. And if you walk up the mast of a ship, you can see a little bit further because you can see around the curvature. The event horizon isn't like that. It's like really a fixed sort of area in space with the black hole within that. And anything that happens in there, there's no way you can move around or do anything to be able to see inside that event horizon.
Right, and then singularity is the middle.
Yes.
What do and don't we know about what that's like in there?
On the show last night, Jess very eloquently put that as the place where maths goes to die, which I thought was great, because it's a point, to the best of our theories, it's a point of infinite density and zero size. Right at the centre. We have good reason to expect that we can't actually have something of infinite density and zero size, but we don't have a good theory of physics that incorporates both gravity and quantum physics well enough to explain that at the moment. And that's one of the reasons that black holes are so interesting, because we're trying to figure out how that behaves, what is actually going on at the centre of a black hole.
Right. So if I'm an astronaut,
yeah.
As I've aspired to be at one point in my
me
life,
too.
who hasn't, and I'm sort of sidling up to a black hole, what could happen? Am I safe?
Well, safe is probably it's a relative word. If you're going close to a black hole, we talk about close to the event horizon of the black hole. As long as you stay outside the event horizon, you should be fine. You can escape, as long as you have a powerful enough rocket. But there's a couple of things that you would want to watch out for. One is, especially if it's a small black hole, actually things are more extreme sometimes near the small black holes. The tidal effects, so the differences in gravity from one place to another, become so strong that your feet might if you're like standing with your feet towards the black hole, your feet will experience gravity so much stronger than your head that your body can get ripped apart. And that's the technical term for that is spaghettification.
Okay, that's pretty cool.
I think is hilarious. But that's one of the problems. And they've actually seen this kind of thing recently with it's one of the things that you expect to see when you're looking at a black hole like the supermassive black hole at the center of our galaxy, if a star comes close, it's going to experience this sort of spaghettification where it will get ripped apart because it's a big thing and one side is closer to the black hole than the other, and it gets ripped apart. And so the star, it doesn't just like swallow the star whole, it sort of stretches it and it will orbit and like rip it apart before it gets swallowed in.
That is violent at a really big level. So we've got someone asking on Facebook, how does time change inside a black hole?
Oh, that would be one of the other fun things that would happen if you ventured near a black hole, because watches tick differently from here out to space. So time runs slowly in a gravitational field compared to what it does in sort of the vacuum of space. And that's such a small effect here on Earth that we don't notice it that much. But we actually do use that because GPS satellites actually have to take that into account because they're up in space, they're in a different gravitational field to us here on the surface of the Earth. And if we didn't take into account the fact that their clocks tick differently to the clocks on Earth, then all of our GPS devices would drift. The accuracy would just go down. We'd drift by about 10 kilometres a day.
Wow, okay, that's really measurable down here.
So even though, it's a tiny amount of time, it's really important for things like GPS to understand this and where it comes from. But the question is, what happens to time inside a black hole?
Yeah. Does the object or person inside the black hole realise that this is happening to them?
No, so there's actually a sort of a dichotomy between what you would see. From an outside, as we see an astronaut, so you're the astronaut, if zooming in towards the black hole, you're going to be the first adventurer inside a black hole. Really bad idea. But anyway, you're going in, and as you approach the event horizon, your clock starts going so slowly that you effectively freeze. So from outside, we just see you sort of frozen going, bye, like not moving anymore, and you just sort of fade because so little light is reaching us from you. But we don't actually see that moment where you disappear across the event horizon. While to you, locally time always ticks normally. So if you're just falling in, you don't notice yourself slowing down. Time ticks normally for you and you just fall in. And so that is what sort of a very different version. You would just fall straight past the event horizon, presumably keep going and do whatever happens at the singularity at the center. But there's mathematically some fun stuff happens inside. You could say, it depends on how you describe it. You might be referring to the thing that time and space sometimes flip inside a black hole, depending on the maths that you use.
Okay, that sounds like a different kind of black hole to potentially go down. We've got another friend on Facebook asking, could scientists observe black holes by throwing a probe into one? Would that work?
You could definitely throw a probe into one, and all you would learn from it is what it could emit before it went across the event horizon. So
same as anything else, really. Right.
So it can't throw light out of the event horizon, and all of our radio communication and that kind of thing is actually just light. So it can't send a radio signal out or anything like that. And so that's not going to help us any more than just sort of what you would see before it fell in.
Right. So you did mention before that black holes aren't sort of just like a giant cosmic vacuum cleaner, but we do have them in our neighbourhood in space, and there's even a really big one in the middle of our own galaxy. Yeah. Is Earth in danger?
No imminent danger to Earth, don't worry. It's all going to be okay. The Earth is just happily orbiting. There's been a supermassive black hole at the centre of our galaxy essentially since it formed. And there seems to be a supermassive black hole in the centre of every galaxy. And by supermassive, I mean millions of times the mass of our sun, up to billions of times the mass of our sun. So these things really are huge. But as long as you don't get close, it's fine.
Right.
It's not going to kill us. Eventually, over time, stuff will fall in, it will grow, and you'll end up with a lot of the galaxy going in until eventually all that's really left of our galaxy will be a ginormous black hole, which will then start evaporating.
Right, so let's talk about that. Yeah. So we were talking about how black holes might feed. If there's no food for a black hole, what happens? Do they die?
Yeah, so black holes actually can die. And this is one of the things where the theory is still a little bit uncertain about exactly what happens, but it's actually the thing that Stephen Hawking is famous for. It's called Hawking radiation. If you sit a black hole in absolute nothingness, so it has nothing left to feed on, just in vacuum, it will emit radiation. Now, seems contradictory to everything I was saying before about the fact that you can't emit light from inside a black hole. But the thing is, what it's doing is the gravity of the black hole is affecting the vacuum outside it.
Mm-hmm.
And through weird quantum effects, there's these pair production in empty space is actually not empty.
Okay.
Yeah, but we won't go down that hole too much. But empty space actually has little particles popping in and out of existence all the time. And if one of those gets sucked in by the black hole, the other one can escape. And essentially what it's doing is it's stealing energy from the black hole after it's been created in order to turn into a real particle and escape. And we could see those particles, like light particles, for example. And when that happens, the black hole gets a tiny bit smaller because it's lost some energy. And so it gets a little bit lighter and starts to shrink. And so that's, we think, in the very, very distant future, the fate of the universe, anything that would have formed a black hole would then evaporate, and it would just be light and particles going out.
So taking that in the other direction, that kind of brings us to another question. What can black holes tell us about how the universe formed in the first place?
Oh, yeah, because the singularity at the center of a black hole is actually... there's another singularity that we think happened, and that's the Big Bang. So that's the beginning of the universe. So I was talking about the singularity before as a place of enormous density, technically infinite density if it's a singularity. And if you think about the universe is currently expanding, but if you put that in reverse, all of the material we see in the universe was once compressed into a really small space. And if you go take it to its logical conclusion there, it ends up being a singularity at the beginning of time as well. We don't know what the beginning of time means. All of our theories again break down, but this is one of the reasons why studying black holes is so cool, because if we can explain what happens at the center of a black hole, perhaps we can also explain what happens at the beginning of the universe, and we might be able to figure out how the universe actually began, which is would be an amazing feat, I think. I'm often just impressed by the fact that as humans we now are able to look out and observe so much of the universe and understand so much about it. I remember I was at a telescope once where we had observed we accidentally observed this really ancient black hole in the very distant universe, and I was like, what is that? I was like looking at the spectrum and I was like, what is that? And my colleague was like, oh, that's an active galaxy, go check that out. And I looked at it and it was a black hole that we weren't seeing the hole itself, we were seeing the material that was falling into it, that was getting really hot, and that glows really, really brightly. And we'd seen that, and it had emitted the light we'd seen more than 12 billion years ago. And to put that in context, the Earth is only 4.5 billion years old. So we're seeing light from before the Earth even formed, and like by a long way. So when I saw that, I pushed back from the desk. I was like, whoa, that's amazing. So the fact that we can see that and understand what it is as humanity, I think is amazing. Now I'm doing a project where we're studying almost 800 of these things spread out over cosmic time and trying to learn how these black holes evolve.
I'm sitting here with Professor Tamara Davis from the University of Queensland. She's taking your questions on black holes, so put them in the comments and we'll ask them to her. One of the questions we've had from Facebook so far is there dark energy inside a black hole?
So dark energy and dark matter are two of the other big mysteries of the cosmos, which I love studying.
Everything's always dark and black.
So they're both called dark because we can't see them. What we do see is we see their gravitational effect. So it's like the black holes. We can't really see the black hole, but we can see the stuff that gets bright as it heats up, as it's falling towards the black hole before it hits the event horizon. And we can also see the black hole, like the one at the center of our galaxy, by the stars that are orbiting around it, because we can see these stars orbiting nothingness. And by how fast they're moving and how far they are from that center, you can calculate how heavy the black hole at the center of our galaxy is. So that's a black hole. But then dark matter is something we also measure by its gravitational effect. So we can see it affects how galaxies orbit each other and how they spin. It affects the whole structure formation of the universe, like the fact that the pattern of galaxies that we see. And that, again, we can't feel it like a particle that touches us. It's not something that we can measure in any other way yet, but we can really, it's blatantly obvious that it's there because you can see the dynamics of the galaxies are dramatically different than what they would be if the gravity was only being generated by the stars and the gas and the bright things that we see. Now, the question was, and dark energy goes even further, because dark energy we think is smoothly distributed throughout space, and it actually is even weirder. It has a repulsive sort of gravity. It pushes instead of pulls. We don't know why that happens, but it's accelerating the entire universe. And that's really, really weird because imagine if we could harness that kind of anti-gravity somehow. We could maybe make new propulsion systems or something. Who knows? But at the moment we don't know what it is, and that's one of the things we're trying to study. So is there stuff in the black hole? Almost certainly yes, but who knows? And we don't really know what happens at the center. So what happens? Does the stuff get destroyed? Does it get compressed into a singularity? We really don't know, and we need better theories in order to be able to figure this out.
So one of the other things we were wondering about is basically every image that we've ever seen of a black hole is an illustration. Will we ever see a photo of one? Will we ever have an image of a black hole?
Yeah, so like we were talking about on the program last night, there's this thing called the Event Horizon Telescope, which was really actually trying to take a picture, an actual image of the black hole at the center of our galaxy. And what they expect to see is essentially a silhouette, because all that they're doing is getting enough resolution, because these things are tiny. Well, you're looking at something that's much smaller than our solar system, that is right at the center of our galaxy, where it's taken tens of thousands of years for the light to reach us. It's like really far away. So you've got to have a really, really good resolution camera to be able to see it. And the only way that they've managed to achieve that is by spreading out radio dishes all over the Earth and looking simultaneously with all of them at the same thing. And by doing that, it's sort of like having a mirror that's scattered all over the Earth. And by putting all of the pieces of the mirror together later, it's constructing what you would have seen if you had a mirror of that diameter. It's not as sensitive, but you have the same resolution as if you had a mirror of that diameter. And that should let them see the black hole at the center of our universe. They've got the data. I don't know what it is because I haven't actually seen it, because I'm not part of the team that's actually doing that measurement. But they're predicting that they should be able to release an image in a couple of months.
That is really exciting.
Yeah, so that's exciting.
So we've been talking a lot about seeing evidence of a black hole through the light that comes to us from across the universe. Yeah. But there's another way we can listen to black holes. Can you talk about that?
Gravitational waves. And until recently, until 2015, we'd never been able to detect gravitational waves. But they'd been predicted a century before, almost exactly a century before. Einstein had predicted that because mass warps the curvature of space, that was sort of his real insight, is that you could explain gravity by curved space. And if you can imagine, like a black hole is like a big funnel of space, it's like a big waterfall of stuff falling in. But if you have one of those here and you have another one of those here and they orbit around each other, then you get essentially ripples coming out because the space is changing, and that propagates away, just as though you've like dropped a couple of rocks in a pond and you see the ripples coming away from that. The same sort of thing happens. And the thing is, space is really, really stiff. It's very hard to bend. It's the stiffest thing we know about. And so the warping that you get is so tiny that they needed to make huge detectors to be able to do it. And it's still an incredible feat. So LIGO is the detector that did it first over in the States, and there was 2 of them. They have lasers that go off in 2 directions, and what they do is they measure the length of the arms of these cavities. They're 4 kilometers long.
Right.
And as a gravitational wave passes through from the ripples created by 2 black holes colliding, these change a little bit, and it's sort of like squish, stretch, squish, stretch. And they detected that, and they found 2 black holes about 30 times the mass of our sun. That was the first detection of this, and that was crazy because we've only ever been able to see things from space. We can't go out and do experiments on it. We can't touch it. We've only been able to see the light and some cosmic rays coming from space, and now we have a whole new way to detect the universe, and that's the gravitational waves, which was pretty cool.
So we've got Professor Tamara Davis taking your questions. Here's a question from Darren. What is the device that measures gravity? How do we measure gravity?
That's a really good question.
Good on you, Darren.
Yeah, no, well, the way that we're doing it with, you step on your bathroom scales. Like, that sort of measures gravity, but that's doing something, it's not measuring exactly the strength of gravity. Like, there's two different ways that you can think of gravity. So there's the absolute strength of gravity. If you have a certain amount of mass, then this strength of gravity will tell you how much the force is from that mass. Here on Earth, we tend to think of, like, our weight when we step on a scale is not the same as our mass, because it just so happens that the Earth is this size, this mass, and that sort of changes how much we weigh. So anything that measures how different masses react to each other. So the way that we measure the mass of the black hole at the centre of our galaxy is by looking at how stars orbit. We can measure the mass of our sun because we know our distance from the sun and we know how fast we orbit. If we were going too fast, then we would fly off into space, and if we were going too slow, we would fall in. And that's determined by the mass of the sun. So at essence, that's using orbits is the way that we measure black hole masses.
So how two things are kind of moving in relation to each other.
Yeah.
We've also got, why is the vacuum of space called a vacuum? Thanks, Aldo. What does vacuum
why
mean?
word comes? But I guess the inverse of that, I don't know where the word vacuum comes. That's a interesting one. But we often relate it to a vacuum cleaner,
right?
And that makes sense because what you do is a vacuum's a place of very, very low pressure where there's almost no particles in there. And the way that a vacuum cleaner works is you make a low pressure piece of air that then, if you've got a low pressure thing in, say, the bag of your vacuum, air wants to rush in, and that's essentially what a vacuum cleaner is doing. And so that's my best answer to that.
So space is a place where there's very little.
Yeah, it's very, very empty compared to the air here on Earth.
So Ernest has got a really great question that I don't quite understand, so maybe you can clarify for all of us.
Uh-oh.
Is a black hole a wormhole where the other side is actually a white hole?
So now this is getting a complicated one. So white holes are theoretically possible. They're sort of the inverse of a black hole. It's when black holes suck everything in and white holes push them out. Okay. Now it's sort of in the mathematics of it, it's basically if you when you take a square root of something, you get a plus and a minus version of it. The black holes are the plus version and the white holes are the minus version. We don't know if they exist in reality, but it's a theoretical possibility.
So a lot of what we know about how black holes work is based on how the maths works, but then we're able to observe more and more things that are confirming what we have inferred from what we've had so far.
I think that the power of mathematics in physics is astonishing because so many things have happened over especially the last century, where for quantum physics, for example, there are multiple times over the last century the maths has said, hey, you guys have seen these protons and electrons and photons and all of these other particles. Our theory describes this, but if that's true, this other type of particle that you've never seen must exist. So people have gone out to try and measure that and gone, whoa, that was right. It actually does exist. And so we're able to predict the existence of types of particles that we've never seen. And similarly with relativity, you're able to predict that time should move slowly on Earth compared to space, and then go out and test that with really sensitive clocks on satellites, and it's true. And then you can predict that you should get gravitational waves, that you should get stretching and squishing from black holes colliding, and then go out and wow, it works. So the power of our theories to explain what we see is really strong, and that's why it's so weird that we've got general relativity doing gravity really, really well, and quantum physics doing all of the particles really, really well, but they're fundamentally incompatible. They can't both be perfectly right. If you want to say why that is, it's because time isn't flexible in quantum physics. But anyway, that's why studying these things is really interesting, because maybe we can figure that out. Who knows what we'll be able to achieve once we do know that.
Right, so we've got Penny asking, Tamara, what's your favourite cosmological phenomenon? Is it neutron stars? Is it supernovae?
Ooh.
You spend a lot of time looking at the sky, so what's your favourite thing up there?
That's a great question. So I really like gravitational waves, but I feel a bit bandwagony saying that because they're
Everyone
just the
loves
new big thing.
Gravitational waves.
The fact that the universe is accelerating, how crazy is that? Dark energy, that's pretty awesome. Maybe, though, it might be the cosmic microwave background, which is this, if you go back in time, the whole universe at one point would have been so hot and dense that if you had lived back then, it would have been like living inside a star, but a star that went to infinity in all directions. Now, as the universe expanded, the galaxies sort of formed in here, and we formed, but that the light from those days is still propagating, and there's something called the cosmic microwave background, which is it's in microwaves now. It's been detected with microwave telescopes, and that's actually all surrounding us in every direction. And it's real confirmation that the universe really was in this hot, dense state in the past, because we can actually see it. And there's a whole bunch of details about that that's really cool. But the fact that we can essentially see light from very close to the Big Bang, to me, is pretty amazing. That might be one of the coolest things.
That's amazing. So, is there a black hole in our solar system? Where's our closest black hole?
So we probably don't know where our closest black hole is precisely. There's a few that have been detected probably by microlensing in our galaxy. Now, and the closest big one that we know about is the one that's at the center of the galaxy. Mm-hmm. So that's Sagittarius A star. And but we expect that there's lots floating around our galaxy. We just haven't seen most of them yet. One of the ways that we can see black holes floating around our galaxy is if the black hole passes between us and a distant star. As it passes between, it acts like a lens, because light falls in a gravitational field. So the light that's traveling towards us would have gone like this and traveled out like that, but it gets bent. And when it does that, it acts exactly like a glass lens that focuses the light. And so the background star gets brighter temporarily. So we can watch this as things are moving, around in the galaxy just sort of slowly. As it passes in front, the background star brightens and fades, and that's how we can tell that there was something there. Not necessarily a black hole. That one could be a planet or something. But if it's heavy enough, then it's possible that it's a black hole, and that's one of the ways that that we can look for them.
We had one of the people who watched last night asking about light having mass. How is it bent by gravity if light doesn't have mass?
Perfect. Good question. So, the famous equation from Einstein, E = mc squared?
I've never heard of it.
No. So what it means is energy is equal to mass times speed of light squared. And it's saying that mass and energy are actually equivalent. In terms of gravity, they react in the same way. So the light is just like, light has energy. It doesn't have mass, but it has energy, and it reacts exactly like it would if it was a particle with mass times c squared, or of the equivalent sort of mass. So yeah, light falls in a gravitational field and can get focused in that way.
We've got Grace asking a question on Facebook. Some clarification. You were talking about space being stiff.
Oh,
can you elaborate?
Okay, so it takes a lot of energy to curve space, and so causing that curvature is really, really difficult, and that's why we're not going to see anything. That's why we don't in everyday walk around just all of a sudden being fatter and then taller and then fatter and then taller because a gravitational wave has passed through. It's like we don't notice it in our everyday lives. If we did, that would be quite interesting. But that's why you need like these huge black holes colliding before it has an effect that's big enough for us to see. And even then, the detectors at LIGO that measured this, they measured the change of length of this arm of the interferometer, or the detector, which was 4 kilometers long. They measured it to better than the accuracy of the size of a proton. So you're reflecting light off this mirror, and the mirror is made of atoms, the center of which you've got protons, and the accuracy with which they measured the distance was better than even like the surface of the mirror. It's an amazing sort of technical feat in order to be able to measure that. But that's sort of what we mean by it's stiff. It doesn't move very much when you push on it.
So if we're talking about singularities, we've got Nathan asking how are singularities measured, which I suppose is, can you weigh a black hole? How do you know how massive a singularity is?
Good question. So you don't have access to the singularity itself. It's a cool phrase in the people early on doing black holes. There was a proposal that all singularities must be surrounded by an event horizon. I mentioned this because it means that the theory is called no naked singularity. You can't have any naked singularity. So anyway, you can't see the singularity, you can't go and poke and pot it. But what you can do is put things in orbit around it, or watch things that are conveniently orbiting it already. And that's how we measure the mass of the singularity, etc.
So we're down to our last question. We've got Hannah asking, can you reverse a black hole?
Not that we know of. I mean, we talked about white holes earlier as a theoretical possibility, and we could venture into the realm of wormholes and whether you can actually, if something fancy in the center could happen in such a way that you could traverse space through effectively a black hole, but it's sort of a wormhole type thing, and come out somewhere else. Again, we can speculate about all of these things, but we can't really say until we have a theory of quantum gravity, because then we can actually answer some of these difficult questions about the stuff that we don't yet know.
So many questions. Thank you so much, Tamara, for joining us today. That's all we've got time for. Thank you so much for watching and playing along. If you missed last night's episode of Catalyst on black hole hunters, you can catch up on iView. We'll post a link in the comments. Bye.